Hi everyone, thank you all for watching my e-talk. I'm Raúl Amaya-Almazán and I'm a Ph.D. candidate at the Instituto Nacional de Astrofísica Óptica y Electrónica in México. I'll be presenting a compilation of multi-wavelength studies of flat spectrum radio quasars CTA 102, 3C454.3, and B21633 plus 382. So the outline of my presentation is as follows. First, I'll give you a brief introduction about FSRQs and why it is important to study the radiation from multiple frequencies and the objective of this kind of studies. Then I'll show you the most important results found in these sources while explaining their consequences. Finally, I'll conclude with the most important findings of these studies. A flat spectrum radio quasar is a type of blazar, which is a type of active galactic nucleus with a relativistic jet pointed towards Earth. FSRQs are composed by a supermassive black hole with a relativistic jet, an accretion disk, an electron plasma also called hot corona, hot clouds of gas called the broadline region, in addition to slower colder clouds at kiloparsec scales called narrow line region. FSRQs present broadlines in their optical spectra, as you can see in the bottom panel of the right figure, in contrast to blazars of Bell-Lac type, which do not show emission lines, at least not with equivalent widths greater than 5 angstroms. So why study FSRQ's emission in multiple wavelengths? This is in order to understand the physical processes and mechanisms occurring in the central engine. FSRQs are very interesting astrophysical objects, since they practically emit radiation at all observable frequencies, from radio to gamma rays, and their optical spectra present broad emission lines. This allows us to probe the different regions of the central engine and the relativistic jet. Flat spectrum radio quasars also present high variability at the electromagnetic spectrum, and sometimes these multi-wavelength emissions are correlated. The low energy emission corresponds to thermal emission mainly from the accretion disk and synchrotron, while the high energy is mainly from the inverse Compton process. The main questions to answer are: where are the gamma rays emitted? Are they emitted from within the central parsec or downstream the jet? Are there multiple gamma ray emission regions? What is the dominant mechanism for the production of the gamma rays? Where are the seed photons coming from? Is the main source of these photons changing? Is there an outflowing broadline region component? If it exists, is it contributing to the gamma ray emission production? Can we use reverberation mapping and or single epoch techniques in order to estimate black hole mass for FSRQs? The gamma ray emission region location in this type of objects is still under debate. Some works show that the gamma rays might be produced within the inner parsec of the central engine, while others have found them to be produced further downstream the jet. However, in these three sources, we found them to be emitted at different locations. So let's start with CTA 102. The gamma ray emission region was found to be located by the quasi-stationary component in the BLBI images of the parsec scale jet, which is located at approximately 25 parsecs from the black hole. This was found due to the contemporaneity of the gamma ray flaring activity of early 2016 to early 2017 and the interaction between a moving component and a recoblimation shock. 3C454.3 is a very active source with multiple gamma ray flares. We define two different flaring periods. The flares of 2010 and 2014 were produced by the ejections of components from the 43 GHz core, which is at 9 parsecs from the black hole. The flare of 2015 was probably a component interacting with the quasi-stationary component. This shows us that this source has multiple gamma ray emission regions. For B21633 plus 382, we performed a cross-correlation analysis between the multiple wavelengths. One of the most interesting results was a significant correlation at a delay of approximately 70 days between the gamma rays and the 15 GHz, which allowed us to estimate the distances between the emission regions of these two wavelengths. Using Monte Carlo simulations, we found a distance of approximately 4 parsecs between the gamma ray and the 15 GHz emission regions. From Pushkarev and collaborators' work, we took the distance from the base of the jet to the 15 GHz emission region, and after performing a subtraction, we found that the gamma ray emission region is at approximately 37 parsecs from the jet apex. So now let's talk about the additional broadline region component related to the jet. From studies of Arshakian and collaborators and Leon Tavares and collaborators, an outflowing broadline region component was proposed to explain the link between the optical continuum, the emission line, and the kinematics of the parsec scale jet. So let's see if these sources presented the evidence of this additional broadline region. CTA 102 presents in their optical spectra the magnesium 2 emission line and the UV ferrum 2 band, which allowed us to study the broadline region. The emission from these two lines responded to the changes of the continuum when the jet was the dominant source of continuum. Additionally, it was found a blue shifted broad component when the flux of the magnesium 2 line was in the maximum flux, which can be interpreted as an outflow. The time delay of 0 between the jet-dominated continuum and the magnesium 2 emission line would locate this additional broadline region at 25 parsecs. For 3C454.3, the behavior of these lines was more complicated. We separated the luminosity relations between the emission lines and the continuum by two different periods. During the first flaring period, the lines responded strongly to the increase of the jet-driven continuum. This would locate the additional broadline region due to the time delay of 0 at 9 parsecs from the black hole. During the flaring period 2, the response was weaker. This could be due to a different ionizing spectrum during this period, or maybe the broadline region changed. For B2 1633 plus 382, we analyzed the profile of the carbon 4 emission line by computing the mean and the RMS spectra. The RMS allows us to isolate the component of the line that is varying. As can be seen in the bottom panel, the RMS is larger in the blue side of the line, which could be interpreted as a broadline region component moving in the direction of the observer. Additionally, during the 2011 period, the luminosity relation between the continuum and the emission line presented a statistically significant anticorrelation. This could be interpreted as the jet stealing the broadline region material and that this broadline region is not dense enough to be easily ionized. So the origin of the different gamma ray flares have been different in these objects. In CTA 102, for the production of the gamma rays in an electronic model, the electrons were accelerated in the interaction between the moving component and the stationary component. The seed photons most probably were produced by the additional outflowing broadline region. In 3C45.3, we have that during the first period there was injection of particles during the ejection of the component from the radio core, which took into higher energies the photons coming from the additional broadline region. While during the flaring period 2, there was a superposition of events. Two of the flares during this period were produced by the ejection of components from the radio core, and the other flare might have been produced at the quasi-stationary feature. Since the emission lines do not seem to strongly respond to the changes in the non-thermal continuum, the seed photons most probably were provided by the synchrotron emission of the jet or from the sheet in a spine sheet model. In B2 1633 plus 382, the gamma ray flares of 2009, 2010, 2012, and 2013 can be explained by the ejection of components from the BLBI core detected by Jorstad and collaborators and Algaba and collaborators. The 2011 flare did not coincide with an ejection. Raitieri and collaborators explained this flare with changes in the Doppler factor due to geometrical effects. However, Algaba and collaborators and Hagenthorn and collaborators found that variations in the Doppler factor were not enough to explain these flux variations. Additionally, we found small changes in the polarization angle, and this is not compatible with the geometrical changes in the jet. So we propose that the flaring event of 2011 was probably produced by magnetic reconnection due to the outflowing broadline region interacting with the jet and causing oscillations at the base of this, helping induce instabilities. So let's now talk about the implication of the black hole mass estimation. Here I show the luminosity relation between the emission line and the continuum respective to each of the sources. The solid lines in these figures represent the relation estimated for the respective relation for a radio quiet sample by Shen and collaborators. Neither of these sources follows the luminosity relation estimated by Shen and collaborators. Reverberation mapping and single epoch techniques require a single line arcing source, the accretion disk, and a viralized broadline region. Neither of these conditions is met by these sources. The use of these techniques with flat spectrum radio quasars might need the use of observations when the continuum is dominated by the accretion disk and a possible spectral decomposition to use only the line component corresponding to the viralized central broadline region. Lastly, the conclusions. The location of the gamma ray emission region cannot be pinpointed in all blazars. The gamma ray production depends on the physical properties and the environment of each source, allowing it to change locations from one flaring event to the other. The gamma ray production mechanism is not simple. A dominant source of seed photons for inverse Compton might change with time. There is evidence of an outflowing broadline region component, which in turn might help the production of gamma rays downstream the jet by providing a new low energy photon field. The evidence of a non-virial broadline region component and the jet being able to ionize these clouds demands considering these facts for the black hole mass estimation through spectroscopic methods. Thank you.